Hello, it's a great pleasure to have this opportunity to talk to the Manchester Literary and Philosophical Society to tell you a little bit about what's going on in the world of astronomy. Perhaps not quite in the environment I'd have wanted to do so, but nonetheless it's good that we have the technology to be able to keep talking about science and for me to be able to give this talk today. Before I get started, just a little bit about me. My name's Michael Merrifield. I'm Professor of Astronomy at the University of Nottingham. Quite a lot of what I'm going to talk about today is related to work that I do for the Science and Technology Facilities Council, which is the research council that oversees major scientific facilities in the UK, including its telescopes. I do quite a lot of outreach related things. So for example, you can find some videos about some of the astronomy that we actually get to do with these telescopes in a channel called Deep Sky Videos. And I do various other outreachy related things. For example, I have a little spin out company called Crystal Nebulae that makes glass sculptures of astronomical objects. So in a shameless plug, if you have a birthday coming up, check out what Crystal Nebulae might have to offer. Okay, so let's start with, I guess, a little bit of history. The use of telescopes in astronomy goes back to Galileo in the 17th century. He's sometimes credited with having actually invented the telescope. He didn't, but he was the first person who really saw the potential for it, for its use in astronomy. So using it to look up with rather than using it to spy on your neighbours with. And because he then had the state-of-the-art technology, a relatively modest telescope, he sort of cleaned up because he was the first person who actually looked at these things. So for example, figured out that Jupiter's moons, as shown here, orbit around Jupiter, so was able to show that not everything is orbiting around the Earth, which got him to a certain amount of trouble. He was able to see that the moon wasn't a perfectly smooth sphere, but had mountains and craters on it, that the Milky Way was made up of stars, all sorts of discoveries. And then, as with most things in astronomy, what we do is we take the technology, we push it as far as we can, we find out all the fascinating things we can, and then we push it that little bit further. And so, for example, Galileo was fascinated by the rings of Saturn and spent many hours trying to figure out what it was that he was seeing there. He didn't quite have the quality of telescope needed to tell what was going on. And the best he could come up with was this idea that maybe Saturn had ears. It clearly had things sticking out the sides, but couldn't quite figure out what they were. That had to wait for really the next generation of telescopes to really see that what he was just about able to see was the rings around Saturn. So that's one of the sort of, I guess, the lessons with telescopes in astronomy, that we push the technology as far as we can. We then push it a little bit further and struggle a little bit to try and figure out what's going on. But fortunately, there's always a next generation of telescopes which will then answer that next generation of questions. Just a little bit about telescopes now. Let's talk about what telescopes aren't for. There's a popular myth that telescopes are about making things look bigger. That's not really the point of a telescope. If you want something to look bigger, you just print it out bigger nowadays, or you use a higher magnification eyepiece in your telescope. It's not really about enlarging things. Okay, so what is the point? Why is it that astronomers are always pushing for bigger and bigger telescopes? Well, there's a couple of benefits that come with increasing size of a telescope. The first is, so forgive the rather crude graphics here, if you think about a telescope just basically as a bucket for collecting light, then just in very simple terms, if you have a bigger bucket, you collect more light. And mathematically, we can express that as the area at the top of the bucket, which is basically the size of your telescope, and the area of a circle is pi r squared, or for some reason astronomers prefer to do things with diameters rather than radii. Pi over 4 times the diameter of the bucket, or the diameter of your telescope squared. So that basically means that if you have a telescope which is twice as big, it collects 4 times as much light, which means you can see fainter things with it. So that's one of the reasons why astronomers are always pushing for larger and larger telescopes. The other aspect is a slightly subtler one, and it's to do with the wave nature of light. So here's a set of waves. In this case, it's a set of water waves, and they're all coming in from one direction, and they're passing through an aperture. And then you're seeing these effects of diffraction as they come out the other side. That basically, when they pass through an aperture, the waves spread out on the far side. And this is a completely universal phenomenon in waves. You can see it if you happen to ever be in one of those little Cornish harbours where the waves are coming in through the entrance of the harbour. You can actually see them spreading out on the far side. But it's all kinds of waves, including light. And the reason why this is relevant to telescopes and their sort of limitations is that if you think about it, all the light, if you think about this in terms of light, all the waves, all the light is coming from one direction here. And when it passes into the aperture of a telescope, it then starts to spread out, which means that instead of the waves all coming from a single direction, they're now all coming from slightly different directions. This creates a limiting factor to how sharp an image you can make with a telescope, in that even though all these waves came from a single point on the sky, so they're all coming from a single direction, they're now coming from a wide range of different directions, which means that when you kind of reconstruct an image of the sky with them, you find that actually instead of all the light coming from a single point, it's slightly spread out. The amount it's spread out by is given by a relatively simple formula, that the angle the light spread out by is related to the wavelength of the light, or the waves, whatever they are. In this case, we're talking about light for telescopes, and the diameter of the aperture that the light has passed through. So in this case, if you made a telescope twice as big, you can see that that would make this number go down by a factor of 2, which means your images would be twice as sharp. Okay, so the advantage of a bigger telescope is you can see fainter things because you collect more light, but at least in principle also you can make sharper images with it. So astronomers go to some quite extreme lengths in terms of this diameter d to really get the sharpest images they can. So here, for example, is the relatively new FAST telescope, 500-meter aperture spherical telescope in China. This is a radio telescope where they've created a dish in a natural bowl. It's a sort of larger version of one in Arecibo. It's got quite a famous radio telescope, where this entire natural bowl in the mountains has been turned into a single radio telescope. So it's huge, like 500 meters across, huge collecting area. Of course, it has certain limitations in that you can't point it in different directions. Well, you can a little bit. These pylons around it actually hold the detector for this radio telescope, and by moving that detector around, and actually in this case by distorting the shape of this, there's a whole system of pulleys behind this radio telescope that allow them to kind of distort the shape of it a bit. It gives them the flexibility effectively to make the telescope point to different parts of the sky, but it is a little bit limited just because it has to be looking more or less upwards in order to work. So that's one way of making your telescope very large, to collect a large amount of light and to get very sharp images, in this case in the radio part of the spectrum. There's another way of effectively making your telescope large, which is that instead of having a single dish, you can have a whole set of separate dishes. So this is Alma, the Atacama Large Millimeter Array, up in the Atacama in Chile, one of the driest places on Earth, where they're detecting radio waves, and actually they've gained in two ways here. They've using very short wavelength radio waves. So remember that formula, the sharpness of the images was the wavelength divided by the diameter. So there's two ways you can win. You can make the wavelength shorter, which makes the images sharper, or you can make the diameter bigger. So they've gone to shorter wavelengths using millimeter wave astronomy, so very short wave radio waves. But they've also effectively made the telescope very big, because the D in that formula isn't the diameter of the individual dishes that dictates how sharp the images are. It's the distance between the largest separation of the dishes. Okay, so although you're not winning in terms of the collecting area, because the collecting area of this telescope is just the sum of all those dishes, in terms of the sharpness of the images you can make, that's actually dictated by how far apart the dishes are. So they've been getting some truly amazing images with this telescope. So here's, for example, is a set of images taken relatively recently with the Alma array of radio telescopes. And these beautiful structures that you can see, they look like galaxies, but actually they're not. What you're seeing here are planetary systems around other stars in the process of forming. So Alma's very good at looking at molecular material, and so you're seeing the molecular gas that's in the process of forming interplanetary systems around other stars. And the angular resolution, the sharpness of the image that this telescope is able to make, means that it can actually resolve these planetary systems in the process of forming around other stars, and we see these beautiful images of planetary systems forming around other stars. Now, this idea of making arrays of dishes kind of reaches its natural conclusion in work that was relatively recently, very recently published from the Event Horizon Telescope, where they were trying to image very close to a black hole in the center of, in this case, the galaxy Messier 87. And remember, the two ways you win in this is you make your wavelength shorter, and they've been pushing this technique to shorter and shorter wavelengths. So they're using, again, millimeter wave radio waves. But the diameter here, the separation of the dishes here in the Event Horizon Telescope, they were using telescopes spread out all around the world, and were combining the data in this exquisite experiment in order to actually see very, very sharp, very, very small scale features, in this case, very close to that central black hole in the middle of Messier 87, which is sort of pushing this technique really as far as we can here on Earth. There's talk of putting these arrays of radio telescopes in space, which will allow us to create even bigger baselines. But really, we've pushed things as far as we can on the surface of the Earth by basically spreading out the dishes across much of the surface of the Earth to create the sharpest images possible. Now, that was talking about radio telescopes and how sharp an image we can make with them. Of course, if we move to shorter and shorter wavelengths, in principle, we can make sharper and sharper images, again, just by pushing this wavelength lambda downwards so that the images get sharper and sharper. So, for example, if we went to optical light, which is much shorter in wavelength, we ought to get very much sharper images. Now, if you actually point a telescope up at a nearby star, which should be a kind of a point-like thing, then the blurring of the image doesn't actually look like this at all. It looks like this. And the reason for this is that we have an atmosphere above our heads. And the atmosphere, although it's more or less transparent, isn't completely transparent. It acts a little bit like a lens which sort of distorts the path of light as it comes through. And because it's not a particularly well-designed lens, it doesn't magnify or sharpen the images. It just basically blurs things around. It's like looking kind of through frosted glass, right there. Actually, you end up seeing this kind of distorted view of the sky above you. And worse than that, of course, the atmosphere is changing all the time, which means those optical properties, which are kind of distorting the light, are changing all the time so that the things kind of jump around. So that's why when we actually look at the sky, everything's sort of blurred out in this horrible mess, and it just keeps jumping around because effectively the sky is changing on a very short time scale above our heads. So it turns out there are two ways that we can get around this problem. One of which is truly ridiculously expensive, and the other of which is just very expensive. So let's start with the ridiculously expensive approach to solving this problem first, which is that you can deal with this problem entirely by putting your telescope above the atmosphere, because it's really, the light was beautifully undistorted for 99.99999% of its journey, and it's just that last little bit as it's passing through the atmosphere, all those beautiful light waves get messed up by the atmosphere, and so we end up seeing this kind of distorted view. And so, yeah, in principle, well, not even in principle, in practice, we've done this. We have the Hubble Space Telescope up there taking beautifully sharp images. We can avoid this problem by putting our telescopes into space. This is a far from trivial thing to do. So the successor to the Hubble Space Telescope, here it is, the James Webb Space Telescope. It was originally supposed to cost a bit less than $1 billion. I believe its current price tag is about $9 billion. So it's an incredibly expensive technological development. And it was originally supposed to be launched many years ago. It still hasn't been launched. The current launch date is about sometime in the autumn in 2021. So we've still got a little while to wait till it's launched. But it does actually seem now to be reaching the point where all the issues that they've identified have been sorted out. And it really will be going up sometime late next year. So hopefully we'll be able to get some beautifully sharp images with the James Webb Space Telescope. That's the incredibly technologically challenging way of doing this. Another way you could try and solve the same problem is by saying, okay, so what's happening is that the Earth's kind of distorting the images of things above our heads. So why don't we just take out those distortions? So, for example, if the light gets bent one way by the atmosphere, if we have a little curved mirror, we could actually take out that distortion and flatten things out again. So actually the light will all then be beautifully arranged, and we'll be able to produce those exquisitely sharp images again. We can do that because we know what shape some things actually are. For example, if there's a nice bright star there, we know that a star is supposed to be a little dot. So if you see it distorted in a particular way, that actually gives you information about what the atmosphere is doing. And in principle, then you can then take out the effects of the atmosphere with another mirror shaped appropriately to restore that distorted image to a point-like object. And then if there's something you're actually interested nearby, like a galaxy, the light from that galaxy will have passed through the same bit of atmosphere as the light from the star. So if you sort the star out, you'll actually sort out all the distortions that have happened to the galaxy as well, and end up with a nice sharp image of that too. Of course, that's kind of far from simple in that, as I said before, the atmosphere is changing all the time on timescales of a small fraction of a second. So not only do we actually have to kind of have a mirror that takes out all those distortions, but that mirror has to keep changing shape. So we need a mirror that's flexible. All of this sounds faintly magical, but it turns out that actually we can do those things, right? It actually works. Let me show you an example. So this is Andrea Goetz's work, looking at the center of our own galaxy, which she was a very recent recipient of the Nobel Prize, this year's Nobel Prize for Physics, for the work she's been doing looking at the very center of our galaxy and studying the properties of the massive black hole that lives there. And the reason why she's been able to do that is exactly because of these adaptive optics techniques that have been developed to allow us to take out those blurring effects of the atmosphere. Turns out it's a little easier to do if you work in the infrared rather than the optical part of the spectrum. So a lot of her work's been done in the infrared. It's also where the wavelengths at which you can actually see the center of our galaxy. But actually the adaptive optics works better at these slightly longer wavelengths because the atmosphere changes a little more slowly and isn't quite as messed up as it is when we try to observe at optical wavelengths. But so here's an image, a very blurred view of the center of our galaxy. But when she turns on the adaptive optics system in their telescope, then what you find is that all those distortions get taken out, and suddenly you get this sharp view of what's going on at the center of our galaxy, which has allowed Andrea Goetz and her colleagues to study the motions of stars very close to the center of our galaxy and infer that there is this supermassive black hole about 4 million times the mass of the sun lurking there. So the technique actually works. We really can take out these effects of the atmosphere. There's one slight further complication, which is I said you need a fairly bright star near the object you're actually looking at in order to figure out what the distortions actually are, and so that you can take them all out. And it turns out there aren't that many bright stars out there, so actually there's only a very small percentage of the sky where there's a bright star close enough to the object you might be interested in to be able to use this technique. We found a solution to that, which is that if there isn't a bright star, we make our own. In that we've figured out how you can actually shine lasers up, and way above our head in the upper atmosphere there's a layer of sodium ions, so just ionized sodium atoms, which if you can tune your laser to excite them to create a little glowing spot. And it turns out this layer is high enough up in the atmosphere, it's actually above most of these nasty turbulent things which create all the distortions. So effectively, for the purposes of trying to take out those distortions, it's in space, it's above them, and so actually if we look at the distortions of that little dot that's created by this bright laser shining up there, then we can take out the effects of this distortion on that. We'll also take out the effects of distortion on anything nearby, and of course because it's a laser we can just point it where we want to in the sky in order to actually create that sort of point that we use for calibration anywhere near any object we're actually interested in. So let me talk a little bit about what the next generation of telescopes hopefully has to offer. So this is not a real image, this is an artist's impression of what the telescope's going to look like. This is the European Large Telescope, sorry, this is the Extremely Large Telescope, the ELT. Names in these things get quite complicated. This used to be called the EELT, the European Extremely Large Telescope. We then dropped the European bit. So it's just the Extremely Large Telescope, following on from the previous generations of telescopes, which were the VLTs, the Very Large Telescopes. We sort of ran out of interesting names, although I should say this is a project I've been involved in for more than 20 years now. The first design we came up with was even more ambitious. So this telescope will be 39 meters in diameter. Vast telescope. The original design we were looking at was 100 meters in diameter. And that had the best name of all. It was called the Overwhelmingly Large Telescope, or the OWL telescope. Turns out that was a little too ambitious, so we scaled back our ambitions. Now we're just looking at a mere 39 meter diameter telescope. To give you a sense of the scale of that, those are people down there. That's a pickup truck. This thing is vast. It's an enormous telescope. It's a huge technological challenge. Let me put it in a little more perspective for you. This is my hometown. This is Nottingham. Nottingham is graced by the largest civic space, apart from Trafalgar Square, anywhere in the country. So this is the square outside the council house, the market square. And it turns out this huge market square is just about big enough to put the telescope in. I wouldn't recommend building it there. As you can see, it tends to be a little on the cloudy side. In fact, we're putting it on a mountain in Chile, but it gives you some sense of the scale of the telescope. It's an enormous structure. I have to say, when I first got involved in this project, I had a somewhat embarrassing scientist's contempt for engineers. You know, it's this kind of a cliche that scientists view engineers as failed scientists. Having now been involved in this project, as I say, for more than 20 years, I have to say I have the most immense respect for engineers. It's absolutely astounding the things that they can do. The idea that you could actually build a structure on this scale, and remember this is a telescope, which means that the mirror, the 39-meter diameter mirror here, made up of lots of individual little hexagonal segments, all have to be perfectly aligned to each other within a fraction of a wavelength of light. All the time, you know, if you point the telescope in a different direction, the pull of gravity is in a different direction, you have to compensate for that to keep the mirror exactly in shape. The wind blows, tries to shake it around. We're building it in Chile, somewhere which is quite prone to earthquakes, so it has to be relatively safe against earthquakes. It's an amazing thing, the idea you could actually even envisage a structure on this scale, let alone actually build it. Let me just talk about one of the technological challenges that we faced. And it's a phenomenon called the cone effect. And actually it comes back to this adaptive optics thing. This telescope absolutely requires those adaptive optics in order to function. It's really going to need that sharpening effect of adaptive optics. And so this is a kind of a schematic diagram. This is supposed to represent the telescope. Okay, and here's light coming in from some very distant object, and the green wiggly lines here are supposed to show the nasty things the atmosphere is doing above our heads. And remember I said that the technique we use is we fire a laser up. It creates a little dot in this layer of sodium 90 kilometers above our head, and then the light from that dot comes back down into the telescope, and we use how that light's been distorted to figure out what the atmosphere is doing, the nasty things that the atmosphere is doing above our head. The slight snag is that it turns out that a 40-meter diameter telescope is sufficiently big, sounds very small compared to 90 kilometers, but it's sufficiently big that we have to worry about the fact that the light that comes back down again comes back in this cone, rather than in, if we were looking at a star a very large distance away, it would kind of come down in this sort of cylinder of light into the telescope. And so we don't have any information about what the atmosphere is doing. Even though light from the star is passing through this bit of the atmosphere, light from our little dot that we created isn't. So we don't actually have information about what the atmosphere is doing, which means we can't compensate for it. There is a solution that was dreamed up to deal with this problem, which is that instead of firing one laser up, we could fire a whole constellation of lasers up, and all pointed in slightly different directions. And then of course we've then filled in all this area, which means that we've got information about everything that's going on in the atmosphere above our heads, that we can sort of figure out, model what the atmosphere is doing and compensate for it when we're taking an image of an astronomical object. This was an immense technological challenge. At the time when we were first thinking about building this telescope, no one had ever done anything like this. Even the single lasers didn't work particularly effectively. So this idea of firing a whole constellation of lasers up was sort of almost science fiction then. We didn't actually have the computing power to figure out, because remember, you have to keep redoing the calculations multiple times per second because the atmosphere is changing. We didn't have the computing power to do that modeling to figure out what the atmosphere was doing in order to compensate for it, to distort this other little mirror in order to take out the effects of the atmosphere. And so actually it was sort of slightly science fiction. But the amazing thing is, of course, technology moves on. The power of computers has evolved enormously. So we now have the computing power to do this. The reliability of the lasers has improved. So actually now, not only was this an idea, it's actually something that we've started doing. So this is almost a test system for the ELTs running on one of the current generation of telescopes, the VLTs, where you can see they're actually firing a whole constellation of these lasers, 1, 2, 3, 4 lasers up. They're actually all pointing, although they seem to be converging on a single point, they're actually pointing in slightly different directions, so that we can do this effective kind of modeling the atmosphere above our heads. And actually it's pointing towards the center of our galaxy. So this is near the center of the galaxy, in order to create nice sharp images by doing these reconstruction techniques. So actually, and this is, so this was what, 2016, this thing was first starting to work. So the technology we've needed in order to make this telescope work, we've kind of been doing all the developmental steps as we've been going along, in order to actually allow us to build this telescope and have it work when it gets onto the sky. So one obvious question is, what are we going to do with it? What new astronomy is it that we're going to be able to do that we haven't been able to do before? The short answer is I don't know, because actually the beauty of a telescope is it's just an instrument, right? And actually what you're going to find with it, you don't know until you look. So part of the fun of astronomy, part of the excitement of astronomy is there are always surprises. Turns out that if you go back and read the case that was made for the Hubble Space Telescope, why we needed a Hubble Space Telescope, it was written in the 1970s. It turns out most of the things we ended up doing with the Hubble Space Telescope and are continuing to do with it are nothing to do with what appeared in that original case. And that's the beauty of a telescope. It's a very flexible instrument that you can use to study things that you hadn't even thought of when you built the telescope. But nonetheless, we can't just say, oh, give us £1 billion to build a telescope and I'm sure we'll find something interesting. So fortunately, there are some things which we know we are going to be able to do with the ELT. And so let me talk just about a couple of them. So one of the things, as you saw from Alma, we're now seeing planetary systems forming around other stars. We have lots of information about planets around other stars, exoplanets. And one of the exciting things we're going to be able to do with the ELT is look at planets orbiting around other stars. Now, it's not going to, this is again an artist's impression. We're not going to get this kind of view of a planet around another star. But what we are going to be able to see is something like this. So this is a simulation of the kind of quality of images we'll be able to get with the ELT. Looking at a relatively nearby star, and a huge amount of work's gone into optimizing this observation to actually get rid of the light from the star. So in principle, you could, if you take an image of something that's got a bright star in it, you could just put a little dot over the bright star to block it out. Turns out that actually the light scatters around the dot, and that doesn't work terribly well. But there are more and more sophisticated techniques effectively for blocking out the light from a particular point in the sky and seeing what else is left. So you obscure as much as the light you can from the star. You can see there's still a little bit of light left over, but it's enormously suppressed. Excuse me, didn't mean to go on to that just yet. It's enormously suppressed. And once you suppress that light from the star, you can start seeing the planets in orbit around it. So in this case, the simulation has put an Earth-like planet and a Jupiter-like planet. Of course, the reason why you can see these planets isn't because they're glowing themselves, but what you're seeing is light from the star coming to the planet, being reflected off the planet's atmosphere and coming towards us. That's why we see the planets in our own solar system. That's why we're going to be able to see the planets orbiting around other stars. And the reason why that's interesting is it turns out that the ELT is large enough that even though it's only a small fraction of the light that gets reflected from these planets, we'll be able to collect enough light not only to detect that the planets are there, but actually to split that light up into the spectrum, into the colors of the rainbow, and study the properties of that spectrum. And the reason why that's interesting is, well, let's have a look at our own solar system. If you look at the reflected light from planets in our own solar system, and see what we see. So for example, here's what happens if you take the light that's reflected off Mars. So the plot here shows how much light there is versus the wavelength. And this is in the infrared part of the spectrum again, but again, you'd see the same thing in other parts of the spectrum as well. And what you can see is that Mars reflects the starlight. So it's reflecting the light from the sun, and mostly the light just kind of bounces off the planet. But you can see that actually there's less light reflected at particular wavelengths. That's because although Mars only has a very tenuous atmosphere, it does have an atmosphere. It's got an atmosphere of carbon dioxide. That carbon dioxide absorbs quite a lot of this infrared radiation. And in particular, in this sort of very characteristic band, in this case at a wavelength of about 15 microns, there's not much light reflected by Mars because any light that hits Mars is absorbed by the carbon dioxide at those wavelengths. So not only can we see that light's being reflected off Mars, but actually we can see just by studying the spectrum that it's got an atmosphere and it's got carbon dioxide in it. So that's Mars. If we move on to Venus, that's the next line up here, we can see a similar sort of pattern, lots of light reflected off Venus. Venus actually has a very reflective surface because of its clouds. And so actually we see an awful lot of reflected light from Venus. That's why it's very bright in the evening sky. But again, you can see this is an enormous dip at the same wavelength. Again, that's because Venus has a lot of carbon dioxide in its atmosphere that's very good at absorbing light at that wavelength. Finally, let's look at the Earth, what you'd see if you were looking at the spectrum reflected off the Earth. And again, it's a similar sort of story. There's a broad distribution of light gets absorbed, gets reflected by the Earth. Again, there's absorption due to carbon dioxide. It's a very dominant feature. But I wanted to draw attention to this other feature here. This absorption feature at about 9 and a bit microns is due to ozone, one of the other constituents of the Earth's atmosphere. And the reason why ozone's interesting is because it's a bit of a surprise it's there at all, in that how does ozone get produced? It gets produced by the interaction of ultraviolet light with oxygen molecules. If you zap oxygen molecules with ultraviolet light, you end up doing some photochemistry which produces ozone. And so for there to be ozone there, you require there to be free oxygen there. And the only reason why there is free oxygen in the Earth's atmosphere is because there's life. If there were no life on Earth, all the oxygen would very quickly get locked up in carbon dioxide and other molecules. But it's only because there's plants that are continually turning that carbon dioxide back into oxygen that there's oxygen in the Earth's atmosphere. So this little dip here is actually a giveaway that there's life here on Earth. Because if you know, the presence of ozone requires there to be the presence of oxygen for that ozone to be produced, and the presence of oxygen requires there to be life that's continually pulling the oxygen out of carbon dioxide and liberating it as oxygen again. So this is what's known as a biomarker. This is something that tells us that there is life here on Earth. Okay, we're going to be able to do exactly the same thing with other planets, right? Around other stars. We're going to be, not only are we going to be able to take pictures of planetary systems, see the planets that are orbiting around other stars, but by analyzing that light that's reflected from their atmosphere, we'll be able to say, okay, there's a couple of planets around this star and that one has life on it because it's got these biomarker molecules in its atmosphere. So we'll actually be able to detect life in planets orbiting other stars with the ELT. So that's one of the things we'll be able to do. Let me just talk about one other thing. Obviously, again, there are many projects that we've thought about we might be able to do with this, but I want to talk about, let's go to the other end of the scale. So that's the sort of, at least astronomically, the small scale, talking about planets. Let's go to the other end of things and talk about the whole universe. One of the things we know about the universe is that it's expanding, right? And that was discovered by Edwin Hubble, who was able to show that the further away things are, the faster they're traveling away from us, which is an indication that if you run the clock back in the distant past, everything was in a very concentrated space. And since then, everything's been expanding since the Big Bang. Everything's been flying apart from everything else. Not that long ago, certainly when I started my career in astronomy, our prejudice, our understanding, our expectation was that that expansion should be slowing down because the pull of gravity should be trying to pull everything back together again. And so we'd assumed that the universe would be decelerating. Subsequently, in the 1990s, it was found that actually that's not what's going on at all. By various indirect lines of reasoning, looking at the brightness of supernovae and the formation of structure and various other sort of indirect indicators, it appears very much that instead of slowing down, the universe is actually accelerating in its expansion with time. And we had to, you know, revise all our ideas and come up with a mechanism as to why that might be the case. But at some level, those measurements, as I say, they're all slightly indirect. They're not directly measuring this accelerating expansion. And in principle, at least, there's a simple way to see whether or not the expansion of the universe is accelerating or decelerating, which is that you look at an object in space and you measure how fast it's traveling away from you. And we can do that through the Doppler shift in spectral lines. So again, looking at the splitting the light up into the spectrum. And then if the thing's traveling away from us, the light will be shifted towards the blue end of the spectrum. The faster it's traveling away from us, the more it's shifted towards the blue end of the spectrum. So in principle, we can measure through the Doppler shift how fast something's traveling away from us. Then you just wait a bit and measure it again and say, you know, is it now traveling away from us faster or slower? Because that'll tell us whether or not the expansion is increasing or decreasing with time. Now, it's rather more complicated than that because individual objects may have other things going on. They may be in orbit around other galaxies or whatever it is that you're looking at. But at least in principle, if you average together a whole bunch of objects, you should be able to say, okay, let's measure that expansion, wait a bit, and then measure it again and see if things are traveling faster or slower. It's a very subtle effect. So here's, you know, how fast things are going away from us versus how far away they are from us. And you can see the speed at which they're going. This is 3 times 10 to the 4. So that's 30,000 kilometers per second. So these galaxies are traveling away from us at 30,000 kilometers per second. And you can do the calculations of, how much, if our ideas about the accelerating universe are right, then how much should that change? And so it's traveling away from us 30,000 kilometers per second. If you come back a year later, how much will it have changed by? The answer is about 1 centimeter per second. So it'll be, instead of 30,000 kilometers per second, it'll be going at 30,000 kilometers per second plus 1 centimeter per second. That's a tiny effect. And it turns out it's too small to measure. Even with an ELT, it's too small to measure. But supposing we average together a whole bunch of galaxies, so actually even if in any individual measurement we can't tell, maybe if we average a whole bunch of different things together, we'll be able to see the effect. Turns out you still can't measure that 1 centimeter per second. But if you wait, instead of 1 year, you wait 10 years, then in each year its speed will have increased by 1 centimeter per second. In 10 years time, it'll go a whole 10 centimeters per second faster. And it turns out that plus, averaging together a whole bunch of data, in my view, is just about enough to actually measure this effect directly. So we'll be able to see whether or not all our ideas about this accelerating expansion of the universe are true. It's a very difficult measurement to make. It's right on the edge, even with an ELT, of what we're going to be able to do. But it's the kind of cutting edge science that we're going to be trying to do with the ELT when the time comes. So let's talk a little bit more about what's happening with the telescope. It is getting built. It was supposed to be collecting light in less than 5 years' time. It's now a bit behind schedule. As with most things in life is a bit behind schedule at this point. It's actually partly down to the fact that, though, as ever with a project on this scale, there were various technical difficulties. For example, it turned out that the mountain wasn't quite as solid as it had been thought to be, so they ended up having to pour more extensive concrete foundations just to make sure that the thing is very secure on its foundations. So that delayed things a little bit, but of course then COVID came along and has actually slowed things down quite significantly. But you can see a telescope is getting built. This is the top of Amazonas, the mountain in Chile, where it's actually being built. Beautiful nighttime shot, relatively recently taken, about a month ago, 2 months ago. And you can see that actually the telescope is beginning to emerge. The foundations are laid, and the telescope is starting to be built. It's very difficult to get a sense of scale on this thing, partly because it's just so big. But hopefully this gives some idea as to how how big we're actually talking about, in that there are some people for scale, and a very wide angle view to try and get the entire telescope in. So we're probably not talking about 2025 anymore. It's delayed probably about a year, maybe even a little more at this point. But sometime this decade, we will have this telescope. We'll actually be able to start doing some of that exciting science that I was talking about. This isn't the only game in town. There are other large telescopes that are also being built, although the ELT is probably the one that's most advanced. So the two sort of international competitors are the Giant Magellan Telescope. Again, both of these are artist impressions. Neither of these telescopes is built yet. So the Giant Magellan Telescope uses a very different technology in that you can see there are sort of a set of petals here. Each of those is an 8-meter telescope. So the largest telescopes we're using at the moment, the largest single mirrors we make to create telescopes with, are about 8 meters in diameter. So this one takes 1, 2, 3, 4, 5, 6, 7 of those 8-meter telescopes and combines them together into a single large telescope, effectively about 24 meters in diameter. So much larger than the current generation of telescopes, but smaller than the 39 meters of the ELT. At the Giant Magellan Telescope, they've actually been making these individual mirrors. So they've got the mirrors. They don't have all the funds they need in order to complete the telescope yet, but they are progressing with the project. That's also going to be in Chile. Then the other competitor up in the Northern Hemisphere is the 30-meter telescope, another US telescope. So the Giant Magellan Telescope is mainly a US consortium with various other partners. Similarly, the 30-meter telescope, led by the US, will be sited in Hawaii, all being well. They've run into all sorts of problems, again, partly to do with cost, partly to do with the fact that there are huge sensitivities with building such a large structure on the top of Mauna Kea, which is a very sacred Hawaiian site. So there's lots of very delicate negotiation going on there. And that, combined with COVID delays, combined with the fact that they don't have all the money they need, means that they're also, looking at probably the end of the decade before they actually have the telescope on the sky. Nonetheless, there will be, a whole series of these telescopes, and quite excitingly, from an astronomer's perspective, there'll be the 30-meter telescope in the Northern Hemisphere and the ELT and the GMT in the southern hemisphere, which means anything in the sky we want to see, we'll be able to look at with one of these giant eyes. So I've talked for quite long enough, so let me just sum up a little bit about hopefully what I've been able to convince you of in this talk. Going back all the way to Galileo, most of what we've learned from astronomy has been possible because of advances in technology. And in fact, technology and astronomy really go hand in hand. That a lot of the advances we've been able to make are related to the fact that new technologies come along, bigger telescopes, better instruments, new detectors. And so actually there is this sort of very close symbiosis between the technology that we have to do astronomy with and the amazing things we've been able to find. The coming decades are not going to be any exception. We have new telescopes, things like Alma, the Atacama Large Millimeter Array, things like the Event Horizon telescope that are already doing truly amazing things. There are other telescopes coming along, and in particular things like the ELT and its other giant optical telescopes are really going to allow us to study the sky in completely new ways, learn completely new things. Some of those things we're going to learn, we have some clue, some idea what it is we're going to learn about. We're going to be able to look for things like life elsewhere in the universe. We're going to learn about the expansion of the universe and its ultimate fate. But perhaps most excitingly, most challengingly of all, there are many things we're going to learn with these amazing instruments where we don't even know what the question is yet, let alone the answer. And that's probably a good note on which to stop. Thank you very much indeed for listening to this lecture.